Large amount of fat, oil and grease depositions into the sewerage system can release high concentrations of solids, nutrients and pathogens to water bodies, which potentially danger to the environment and public health. Serious global environment issues such as climate change has drawn public interest to the use of biofuels due to the high compatibilities with the current infrastructure. Inedible biodiesel feedstocks are more favorable than edible feedstock because the sufficient amount of edible oils both for human consumption and for biodiesel production is not produced in most countries. Fat, oil and grease takes center stage as an alternative raw material for biodiesel. Using inexpensive lipid feedstock as raw material will incredibly enhance economic viability. Generally, fat, oil and grease is categorized as oils and fats that are mainly composed of triglycerides and low amount of free fatty acids. Therefore, biodiesel synthesis from fat, oil and grease, trans-esterification and esterification should be simultaneously conducted. However, there is no study of esterification and trans-esterification of fat, oil and grease to produce biodiesel.
The conventional esterification of free fatty acids and the trans-esterification of glycerides are often conducted in homogeneous acid or alkali catalysts. However, there are two major technical issues regarding the use of these two methods. Base catalyzed reaction, for instance, often produce low biodiesel yields, and the operation of acid catalyzed reactions are just too slow. To overcome the technical challenges, trans-esterification with supercritical alcohol was proposed. The use of supercritical alcohol method for trans-esterification was able to produce high yields of biodiesels. However, other problems arise. Now, despite of the high yields of the biodiesels, two separate studies conducted by two groups of researchers in 2016 revealed that the use of supercritical methods requires both high temperature and pressure. This results in a high operational and capital cost. Hence, the development of economically viable process for synthesizing biodiesel is highly desirable. The study conducted by Lee et al. In 2017 focused on the simultaneous conversion of triglycerides and free fatty acids in FOG into biodiesels by thermally induced esterification and trans-esterification on silica in a short amount of time. The positive outcomes of these studies will not only potentially allow FOG treatment to become much more integrated, but it will also provide a promising alternative renewable source for biodiesel.
Now, I'm going to explain about the methodology. The FOG sample used was the Food Waste Recycling Wastewater from the Environment and Facility Management Office, Jeju. The FOG sample was divided into two parts, which is FOG high and FOG low, and each part was separated by a separatory funnel and was stored separately. There were two methods conducted in this research, which is the characterization of FOG and the production of FAMES from the FOG samples. For the characterization of FOG, thermogravimetric analysis TGA was used by using 10 mg of FOG high and FOG low samples with ultra-high purity nitrogen gas at a flow rate of 100 ml per minute. The test was conducted at the heating rate of 10 degrees Celsius per minute from 25 degrees Celsius to 900 degrees Celsius. Next is the production of FAMES from the FOG samples. For this analysis, the FOG samples are mixed with sulfuric acid and methanol and stirred at 100 rpm at 60 degrees Celsius for 4 hours. Silica were loaded in the Swagelok bulkhead union. Then the bulkhead was sealed by two plugs. After that, it was heated to a target temperature from 240 degrees Celsius to 390 degrees Celsius using a temperature programmable furnace at the ramping rate of 30 degrees Celsius per minute. Then the bulkhead was placed in an ice bath and the reaction products were collected by 3 ml dichloromethane. Then a qualification of FAMES was conducted using GCFD. The total FAME yield was calculated based on the overall mass balance.
Results and discussion. To figure the compositional differences between FOG low and FOG high, TGA tests were conducted. For FOG high, there are three distinctive mass decay at 3 temperature. FOG low, there are 4 distinctive mass decay temperature. First is 90 to 150 degrees Celsius, while the other 3 temperature was the same as FOG high. Estimate the effectiveness of thermally induced simultaneous esterification of FOG samples, conversion of FOG high and FOG low to typical homogeneous acid was carried out, and this reaction produces FAMEs, fatty acid methyl esters, with 27.7% FOG high and 9.2% FOG low yield. Figure 4a presented the total FAME, fatty acid methyl esters yield in a function of temperature of thermally induced esterification of FOG high, and the highest FAME yield was reached to 83.4% at 380 degrees Celsius. Figure 5 showed yield of FAMEs as a function of temperature for thermally induced esterification of FOG low. Figure 5a showed highest FAME yield for FOG low was 74.1% at 350 degrees Celsius. The results show 83.4% of FOG high initial mass and 74.1% of FOG low initial mass could be converted into FAMEs. Thus, considering amount of impurities in feedstocks, total FAME yield from FOG high and FOG low were 86.2% and 86.3% respectively.
Fats, oil, and grease have been a long-due issue in wastewater treatment. Accumulation and deposition of FOG in several systems causes blockage to the piping and drainage system, besides affecting the performance of wastewater treatment at the facilities. FOG is collected in primary treatments of sewage treatment facilities and disposed of as landfill, or it can be recovered through saponification. Recently, scientists have discovered the great potential of FOG as biodiesel. Conventionally, conversion of FOG into biodiesel is time-consuming and involves high operational costs. From this study, we learned that FOG can be processed into fatty acid methyl ester, FAMEs, or commonly known as biodiesel without pre-treatment such as heating to remove moisture. Besides, simultaneous esterifications of free fatty acid and trans-esterifications of lipid through thermal induction were achieved. This study has accomplished a total yield rate of 86% in a short period of time. This increases the operational efficiency of the process where high yield of FAME can be obtained in a shorter time. Not only that, thermally induced simultaneous esterification and trans-esterification process has a high tolerance towards impurity found in FOG. This suggests that the waste materials such as FOG from grease interceptor and grease trap from household and industry could be an excellent raw materials for generations of biodiesel. Thermally induced simultaneous esterification and trans-esterification process is economically viable as it reduces the operational costs and material costs in generation of FOG-derived biodiesel. Utilization of FOG as biodiesel is a sustainable development of green energy. Generation of biodiesel from FOG involves conversions of waste material into valuable and renewable resource. FOG-derived biodiesel provides an alternative to reduce fossil fuel dependency as we are facing its depletions. Not only that, FOG-derived biodiesel produce lesser greenhouse gases, thus reducing carbon footprint. FOG-derived biodiesel is considered as a clean green energy that drives sustainable development, at the same time improvised wastewater treatment management.